Start. Welcome everybody to 52 Living Ideas. So today I am delighted to have Stacy Harris with us, and we're going to be talking about a topic which is very close to my heart. I grew up with mathematics. Mathematics is the first thing I fell in love with, math and physics. So it has a very special place in my heart. And then I got interested, I was in technology, and then I got interested in humanities. And I found very odd things that there are people who are aware of the math culture or the science culture, and there are people who are aware of the humanities culture, and many times they don't talk to each other. Also, I found that after doing my master's, I went back to studying mathematicians. I tried to read, Newton in original, Archimedes in original, and I found what mathematics was completely different from what I was taught. And the sense of mathematics, what it is to do mathematics, what does it mean to think mathematically? I don't think that is well understood. So that's what we want to talk about today. And so Stacy, you want to introduce yourself briefly?
Sure. Hello, everyone. So my full name is Charles Stacy Harris III, but I just go by Stacy because the other is just way too much to remember. As Shrikant pointed out, I have a background in mathematics. I currently work doing software design and development with Microsoft, and I do everything development related. I've done everything from tiny embedded systems to large scale cloud systems, but I do have a passion for mathematics and a passion for education and for teaching math. And I work a lot with students. We work with especially minority students. We work with girls. We work with all kinds of student groups. We've had some work with older people who kind of want to go back, and we call it the mature geek. Want to go back and learn some things about math or computer science. And so those are really the things that I focus on. So day to day, I do more software development than anything. Like I said, I have a background in mathematics. I call myself a little bit of a rusty mathematician because I do still do quite a bit of it, but it's not what I do professionally on a day-to-day basis, although it does apply quite a bit to my profession.
So tell me a little bit about how you started out with mathematics. Why mathematics? What was your first?
It's always been sort of in the background, even before I knew what it was. I was really a science fiction geek as a kid, reading things like Asimov and watching Star Trek. I was born in the 60s, so mid 60s, and watching Star Trek and things like that as I got older. So those things always kind of fascinated me. And there was actually a book, I think it was Robert Heinlein, it was called Have Spacesuit Will Travel. And it was kind of funny because there's a kid in the book who wins a spacesuit from some soapbox contest. You can tell it's really sort of 1950s because I didn't even know what that was. I had to kind of look that up. And he makes the spacesuit functional again. And I follow along with him on all of the science. And some of it, you go back and you look at it, and it's not super precise, but it didn't really matter. But going back and following how he made this thing functional, and then, of course, he's out testing it. And as soon as this happens, a spaceship shows up, of course, and he's off. And he's trying to figure out, well, where is he going? How fast is he accelerating? He figures based on how fast they're accelerating and when they do this sort of what's called a skew flip, but basically flip and start to decelerate. And doing all the math for this, figures out, oh, they must be taking me to Mars. And so I actually, in the book, the kid talks about using slide rules and things like that. I actually taught myself to use a slide rule. And I went along and followed along with these problems that he was solving because I just thought it was really cool that somebody had that kind of power, that just using your mind, you could figure things out like that. All the while, of course, thinking that I was bad at math because I wasn't doing that well in school with math. I went to Catholic schools, and they are very particular about the way that you do things. At least they used to be in the past. And I found that the way I did arithmetic at the time was not the way that it was taught in school. And I would get answers wrong. And I would just say, well, I'm just bad at math. But really what I equated at that time in my life, math to, was arithmetic. And the rest of that stuff, the logical thinking and doing calculations on a slide rule and doing algebra and understanding the physics of things, the mathematics of the physics, I didn't really equate that to math in my head. And those things I really enjoyed, but if you said, oh, math, I would say, oh, I don't really like that. I'm not good at it. In about ninth grade, I had a teacher who was giving us back an algebra, a pre-algebra exam. And he said, hey, you're really good at this. You should get a calculator though. And I said, well, what are you talking about? And he said, oh, well, you really understand the algebra part of it, but you keep getting the answers wrong. You keep making silly mistakes calculating. And I said, well, that's because I do it differently in my head. And he asked me to show him, and I showed him that I go left to right instead of right to left. Now I can actually do it either way. And he said, oh, yeah, that's called the Russian Peasant algorithm. And I said, what are you talking about? And he said, yeah, that's a way to do it so that you don't have to write down intermediate results. You can keep that in your head and you can do the whole problem that way. And I thought, wow, that's pretty cool. He said, well, you can either do that, do your arithmetic that way, or just get a calculator. It'll be fine. I opted for just get a calculator and became somewhat of a calculator geek, actually. But I found that after that, I really blossomed. And by 10th grade, I was doing pre-calculus and then calculus. And by the time that I graduated, I actually graduated early because I was a young student, but I also skipped a grade. By the time I graduated, I had done advanced placement calculus, advanced placement physics. I also done advanced placement English, but neither here nor there on that one. I mean, it helps because it's kind of the way I think about things. We'll talk about that. Mm-hmm. But just that approach, that idea that that there was some other way to do things, another way to think about things, to me was just incredible. And that was a change in my life. It was a big, we'll call it a switch in my life.
Yes.
Reference to the last podcast.
Yes. So let me take up now, let's talk about the nature of mathematics. You talked about most people equating mathematics to arithmetic.
Right.
What happens, what leap is involved in going from arithmetic to algebra? What is the idea of having X, thinking in terms of X? What does that do? Sure.
And that leap that goes from just sort of the idea of counting. I think the first thing that we do, then there's actually I think a fundamental leap that happens sort of, I would call it slightly before that. And it'll take you to algebra and geometry and a bunch of other things. But the leap is one of abstraction. So I have a couple of analogies in my head. One is I'm a farmer and I'm out counting and I've got 3 chickens and 4 cows. And I care about that. But when I go to describe that to someone who wants to know how many animals I have, there's an abstraction there. Now I don't go around saying every time I have 3 chickens and 4 cows, I would say I have 7 animals. And what I've done is I've taken a property or a category, if you will, of chickens and animals and how we think about them. And they have lots of different properties. And I've created an abstraction. I've said, oh, I only care for the moment about the idea that they are all animals. And so I would tell you, I have 7 animals. Now, if I needed to figure out something else, maybe I have goats and other things, maybe I need to know how many animals I have who graze versus those who eat from a trough or who are given feed. Those are different properties, slightly different abstractions on those objects, on those animals. And so I would count them differently based on those properties. But the notion of an abstraction is really what the key is. Now we can take that abstraction a bit further and say, there was this time where I was counting animals and I said 3 chickens and 4 cows. Now I'm counting how many tables and chairs that I have. And it's interesting because I have 3 tables and 4 chairs. And now I can say 7 pieces of furniture. And I notice in my, the caveman primitive brain that I have, whatever, I notice in my primitive brain that, wow, that 3 and that 4, that was sort of, that didn't change. I had 7 things. So the abstraction now becomes, oh, well, anytime I have 3 of something and 4 of some other thing, assuming that I care about that property of them sort of being the same, I can add that 3 and that 4. I can replace chickens and cows with tables and chairs, and it still works. What trips many students up, and almost anybody can follow that, what trips up almost all students, and part of this is due to the way it's presented, is that when I stick an X and a Y in for chickens and cows, now this is way too abstract for me. What do you mean X and Y? What are those? I need to know that. Well, you don't actually need to know that to solve the problem. But I think enough sort of sequence, enough repetition for people to start to see that there is a pattern here, and they'll get that abstraction eventually. They'll say that, oh, I understand that I can just stick anything I want in there, this X, this unknown, and I can have multiple unknowns, and some of them might be related and some of them might not. So that's, I think, the big leap, is that notion of abstraction.
So would it be fair to say that instead of focusing on concretes, you are now focusing on patterns between concretes, and your attention is focused on the commonality of patterns?
Absolutely, yeah.
Okay.
Yeah, I think it is absolutely correct. Now what I care about, getting a message that my internet connection's unreliable, sorry. What I care about is patterns and properties of these things. So what are the patterns? How are these things related to each other? That's a really big part of it. Absolutely.
Okay. So what would you say is mathematics? What is mathematics?
Oh, it is so hard to define. It is really difficult. And I think you're going to see there are so many different definitions. Mm-hmm. It starts with things like the concept of number, concept of mm-hmm. counting. That's a really big part of it. And that's I think where all of mathematics really started, was this notion of quantity. Mm-hmm. Quantity very quickly evolves from discrete quantities, how many things you have, so I have 1, 2, or 3, to continuous quantities, how much, 1.5, 1 cup, 1/4 of a cup, 3/4 of a cup, somewhere in between. There's a continuous quantity versus a discrete quantity. So it really quickly evolves into that. But then we start to see other things where we start to measure, and we start to look at shape, and we start to look at all of these things that you can somewhat quantify or think logically about in some way. So you start to, like, for example, if you take a geometry class and you're spending a lot of time with shapes and figures and things like that, and less so with some of the other concepts, but those are the kinds of things that we start to but so there's an interesting definition that I think is probably the most accurate, but probably the least satisfying to someone looking at it from a certain standpoint. And that is, mathematics is what mathematicians do. It's just, because it changes, it evolves. But there's no single approach to mathematics either. So there's no single definition that's completely encompassing.
Got it. I mean, the one that I end up using most in my head is from Kevin Devlin. I really like his books. Mm-hmm. And he calls it science of patterns.
Yeah.
So let's come back to mathematics. So what is it that mathematicians do? How do they look at a problem differently than, let's say, a non-mathematician?
So I think part of it is that we try to formalize our abstractions in a different way. And you'll see actually different approaches to that even. So once you have that abstraction and you have this notion of, and we were to talk about this, operations or processes, right? So the things that I can do that work across the board. So that notion of, addition, for example, doesn't matter if they're cows and chickens or furniture, I can add them. Abstraction over type. What type of things do I have? What's the structure of those things? How do those things change? Mathematicians approach that in a formal way. Well, mostly. So there is sort of the intuitive approach to mathematics. This idea of using intuition and making, sort of intuitive arguments. There's the logical kind of approach of let's, reason over it in a way that we agree is logical. That in itself can be problematic because you and I may not have the same agreement over what constitutes logic. Although for the most part, there's broad agreement. If you look at logical thinking, for the most part, there's broad agreement. Then there's this sort of constructive symbolic approach that says none of that actually matters. What matters is you define a set of symbols and you define a set of self-consistent operations over those symbols. And anything that you can then do within that system is mathematics. And that's, like I said, a more kind of constructive, formalistic approach that you'll see. And there are a lot of sort of famous examples of that throughout mathematics.
What I would like, sorry, go ahead. Please go ahead.
So one of those is actually, it's kind of funny. When I was studying in school, we were studying a mathematician named Kurt Gödel. German mathematician. And I was in a pretty small class, but I would go to the library and all of the books, the translations into English were checked out. So being intrepid, I grabbed the German translation and slogged my way through it, not knowing any German, but reading enough of the syllables to say, oh, I kind of get what that means, and this is a similar word, and enough of the symbols to understand kind of what was going on. It wasn't a perfect thing, but it was kind of fun when I was able to actually make a little progress doing that, not a lot. But if you look at what Gödel looked at, he looked at, and I'm going to try to make this not super technical because I realize that I'm rusty at it and the audience may not all be super technical, but what he realized and what he formalized is that any of these systems that I described that way, where you have a set of symbols and a set of operations over those symbols, that at a certain point, that system can be used to describe itself in certain ways, but there are certain things that may be true in that system that can't be proved in that system, or may be false in that system that can't be proved false in that system. So there's sort of an incompleteness, which is why it's called his incompleteness theorem, in a system like that, in a formalism like that. And by the way, if there are other mathematicians on who have a better way of describing that, my way might be somewhat flawed, but the notion is that idea of being able to describe mathematics using mathematics can lead to this kind of incompleteness.
What I want to do is I was planning to take up this concrete example later on, but I want to prepone that and do it now because I want people to be able to see, what kind of things, I want a kind of a concrete example so they can think about how they would think about it. And then you can talk about how you thought about it. I really liked your description of the 8-queen problem. Can you describe the 8-queen problem and then talk about how you solved, what was your solution for it, and then we can draw lessons from it and see what is being done in the solution of the problem. Please go ahead.
Let's start with a warm-up problem before we go to the 8 queens one, because I think the warm-up problem will kind of give you an idea. The warm-up problem is still a chessboard problem. So hopefully everyone on the call can sort of imagine, or even go out and do a Bing search and pull up a picture of a chessboard or a checkerboard. We'll start with that. And then we take that chessboard, which is an 8x8 grid of squares, and we're going to take dominoes. So again, hopefully everyone knows what domino is. It's this sort of rectangular thing. And let's say that each domino can cover 2 squares on the chessboard. Pretty easy to imagine. We can bring up pictures if we need to, but pretty easy to imagine. If I start laying dominoes across the chessboard on the top, since each covers 2 squares, I'm going to lay 4 dominoes across, right? And I can continue to do that across every row on the chessboard, completely cover the chessboard in dominoes. In fact, if I really want to, I can switch some of those dominoes up. So some are going horizontal, some are going vertical, maybe parts of different rows, some of each. Really pretty easy thing to do. Now, what I want you to do is take a coin, put it on the upper left corner of the chessboard, and another coin on the lower right corner of the chessboard. So now that kind of removes those from the problem. No domino can touch those corners where the coins are. Now start laying dominoes across the chessboard again, and tell me if it's still possible to completely cover the chessboard in dominoes. The way a non-mathematician might approach this, and I'm not saying that you have to be a mathematician to come up with this solution, but the way many people would approach this is they would cover those up and they would start laying dominoes down to try to figure it out, just brute force, without really looking at the full situation. There's some more information in this situation that once you realize, you can instantly solve this problem. You don't need to go any further. Now, if you're sort of clever and you have some computer programming background, you might even try to write a program to figure this out or whatever. I've seen all kinds of people trying to solve this problem. But what is a property of the chessboard that we care about? Well, one of the things that we know about is that the squares are different colors. Red and black, or black and white usually. And if you take a look at the 2 squares that I removed, the upper and lower squares, they are the same color, right? Now, let's go back to what happens when I cover horizontal or vertical. I can't go diagonal with the domino, but horizontal or vertical, when I cover a square on the chessboard or set of squares, I'm covering a red and a black one, or a white and a black one every time. Every domino covers one of each color. So that means that if I've taken 2 of the same color out, to say 2 white, there's still going to be 2 black left. So now, no matter what I do to lay dominoes out, since they cover black and white, black and white, black and white, when I get to the last domino, there are 2 black squares. Domino will not cover that. So what I've done is I've looked at a property of the chessboard that you may not have thought of initially, or if I had just drawn that square with no color at all on it, that you may not have ever thought of. But by looking at that property, I can instantly say that, oh, when you remove those 2, there's no way to cover this. That's mathematical thinking. We didn't do any numbers or equations or calculations. Nobody had to add, subtract, multiply, or divide anything. But that's the kind of mathematical thinking that I'm talking about. And there's some technical terms that go with that. It's parity and things like that. But
so Stacy, let's take a minute to look at. So what did you actually? What did you do? So you looked at a property of the chessboard.
Yes.
Saying that the black and white squares are right next to each other.
Yes.
And because 2 of the same color have been removed, there won't be. So it's you saw a pattern about that, identified that, and said, given this pattern, you also observed that the pattern that each domino has to cover one black and one white square.
Yep.
So you compared those, given those two patterns, you did not have to actually go and concretely put down the concretes to see whether that was possible,
Right.
to try out multiple combinations. Just by comparing these two patterns, you say there will be two squares that will remain empty.
Exactly. By just reasoning over these properties, these abstractions, I can come to a concrete conclusion.
Perfect.
And that's really the key. And it's like I said, it's sort of interesting because it goes back to what I call my sort of fundamental principle when I'm teaching, when I'm tutoring math. The fundamental principle, which I always say, is what do you know, and what do you know about what you know? How do those things relate? What's the meta of this? What's the thing that's just above that that tells me how I can combine and transform the things that I know to get a result?
So how would you ask those two questions for this particular problem? How would somebody ask? Yeah.
Sorry, say that again.
Those two questions,
mm-hmm.
How would you ask that about the dominoes in chessboard?
Sure. So the things that I would ask if I were tutoring a student, I would say, well, what do you know? And hopefully that the student will come up with, well, the chessboard is 8 by 8. They might even, multiply it out and say there are 64 squares. They might figure out that the squares alternate in color. They might figure out that a domino covers a square of each color, whether you put it horizontally or vertically. They might figure out that you can't place a domino diagonally. That's sort of not allowed by our rules. Those are the things that they know to start. And then hopefully they would observe that when we remove those two squares from consideration, that they are the same color. And so that's kind of the thing that we would hope. And now, based on that, be able to reason through. Now, in mathematics, we would talk about there's a concept called parity, where we can actually formalize this whole thing to not just chessboards, but other types of things. And we would talk about it in these terms. If I were to, as an example, assign a value, let's say -1 to white and +1 to black, and then I sum up all of the things on the chessboard, I'm going to come up with the 0 as the sum. And anytime I remove a square, I change that sum, I change the parity. And depending on how I remove squares, I may still have 0 as my number. If I remove a black and a white, let's say I move that first black and white square, I can still cover the thing with dominoes. I have preserved parity. But if I remove two squares that are the same color, I've shifted my parity. And so there's a whole bunch of those types of things where we have things that we call parity preserving operations and other stuff. I think it's a little technical. I wouldn't do that with this. I wouldn't necessarily introduce that term to a student right away, especially when they're sort of just learning abstract thinking. But so you can see how it gets pretty powerful pretty quickly.
Yeah. So let me try to again see what is going on here when we are assigning numbers. So what you're doing is that we are coming up with a new representation for the numbers, and then we are looking at a property of that. So when we addition property, when you add all of it, it is 0. So then immediately when you say, okay, these two are removed, now the sum is not 0.
Right.
So you're trying to kind of use a representation plus, so that's another okay. So can we go to the eight queen problem? Okay.
Yes, and this is actually an interesting one in representation, and the notion here is when you represent a problem, there can be a lot of extraneous information as well. For example, in the other one, we didn't really care necessarily how many squares there were, just that it was an even number and we could cover it with dominoes. It could have been 4 by 4 or 6, whatever. Could have been something else. But the 8 queens problem is a little more interesting. By the way, that first problem was presented by Martin Gardner in Scientific American. He did a whole bunch of math puzzles we'll talk about later. But the 8 queens problem is a sort of classic one. If you know how chess pieces move, queens can move on the chessboard in horizontal, vertical, or diagonal. So they can move pretty much any direction. What stops the queen from moving is a piece of her own color, or if she captures a piece of another color. That's what sort of stops the queen moving. So what I want everyone to imagine again is back to that chessboard. Let's say we have a row, the very top row of all queens. And just to make this more fun, it's a rainbow of queens. They're all different colors. What that means is that any of those queens can attack any of the other queens if they're on the same row, the same column, or the same diagonal. So if I lay them all across the top like that, there's already queens attacking each other. If I lay them on a diagonal, they're attacking each other. So the question is, can you come up with a way of arranging the queens on the board so that no queen is attacking any other queen? And starting again with an 8x8 board, 8 queens, and you just put them on the board in some arrangement. So now back to how would someone solve this? The brute force way is just try it. Just sit down with the chessboard and some queens. I've actually seen people spend quite a bit of time doing that, which is fine. And you just move them around until you come up with an arrangement that works, or you decide to give up and either declare that there is no arrangement that works, which, by the way, doesn't really work unless you've tried all of them, or you just say, I don't know. So that's sort of the first approach. And there's a systematic way to do it if you really wanted to get kind of crazy, but it'll take you really, really, really long time to do it systematically. Enter computers, where someone might try to write a computer program to do the same thing. And with a computer program, the naive approach would be, again, to try all possible configurations of that board, which will take quite a bit of time to do that. So that's sort of the first part of it. Did you want to add anything before I go on?
No, this is good. This is a good description of the problem. Go ahead.
Okay. How I solved the problem was interesting, because I actually solved this using computer, but a friend of mine who was in a computer science class was working on this problem, and they were using a language called Lisp, and they were programming what's called a tree searching algorithm. And please, if you're not a technical person who's on the call, don't let that stop you, because it doesn't matter a whole lot. The idea is that you start with a board configuration, you make a change to that board configuration, and you kind of, basically that makes another node in this list or tree, right? And then at some point you may back up and come back to your starting configuration and try something new. So I might try to move the second queen in the column 2 queen, and say, oh, that didn't work, back it up and move the third one, and say, oh, that didn't work, back it up, move the fourth one. And then sometime later, I might move the second one and the third one. And if that didn't work, back it up and move the second and fourth. So it's all like, you just try and try and try. And so there's this whole algorithm for doing this. And so my friend was saying they were working on this in school, and they ran this program. It ran for 20, 30 minutes, some long amount of time, and came up with a solution, with one solution. And he was clever. He said, oh, we were really clever because there were a whole bunch of essentially paths that we can prune out of our search. Like, as soon as you go to, oh, I moved the second queen down and that didn't work, any path that leaves all those other queens in place, like moving the second queen to the third, fourth, fifth, sixth, seventh, or eighth, right away not to try those. And his program was really clever. It got rid of those, but still took half hour, we'll call it, to find a solution. So when I looked at the problem, I said, I wonder if there's a way to encode this differently to just automatically eliminate a whole class of possibilities, a whole bunch of things that I just don't even have to look for. So this is a little technical. And if you have a piece of paper in front of you and you draw this out, it's great. But if you draw the chessboard and you start to number it, usually in the computer world, if you're a programmer, you're probably going to start with 0, 1, 2, 3, 4, up through 7. If you're not, you're going to start with 1 and go through 8. So let's just do that for the normal folks on the call. But you start numbering the rows and columns from, say, the lower left-hand corner. And so along the bottom, you write 1 through 8. And along the left side, you write 1 through 8, going up to the top. So just do it that way so everybody's consistent. Now let's stick a queen on the board. I can actually now say, based on where that queen is on the board, I can give it a coordinate, if you will. I can say what row and what column it's in. So if the queen is all the way at the top left corner, then it would be in the 8th row in the first column. And you could write that any way you want, 8, 1 if you want it, or 1, 8 if you want to go row first. But what's really cool about it is that if I just look at that bottom row on the chessboard and I just write an 8 in there, that's enough information because I've written it in the cell, in the column where the queen is. So now if I go over, let's say, to the second one, and there's a queen in my second space over on the bottom, so my second column, and there's a queen in the 5th row, I can just write a 5 down there, and that's good enough. In fact, if I just do that across the board, bad pun, across the board, the numbers on the bottom then really become the only representation I need. Now I just write in a number on that bottom of where the queen is somewhere up in the board. I can just actually just chop the rest of the board away and look at that bottom as just a list of numbers. So it's a clever way of encoding the board position. What's clever about it is that it immediately means that that you can eliminate a bunch of things from consideration. So if I only ever write a unique number in the bottom, so let's say I never write 8 twice on the bottom, now I know that the queens are never in the same row. And because I'm only writing one number in that column, I know the queens are never in the same column. So now I can just mix those numbers up, or what we call permute them, create a permutation of the numbers 1 through 8 down there, so that the numbers, again, never repeat. And essentially what I'm only having to check is if the queens are ever on the same diagonal. So by now my next clever bit was to find a permutation algorithm, or in my case, I just came up with one that was pretty fast, that would create these permutations without repetition and without wasting a lot of computer resources. Now, I didn't have Lisp and a mainframe like my friend had. I had a PC at work that had a Pascal compiler on it. Pascal is just a programming language. And so I coded the thing up and I tested it. And in about a second or less, it spit out a whole bunch of solutions. And of course, I go back and I look at this and realize, oh yeah, that one's a solution, that one's a solution, that one's a solution. So it found all of the possible solutions in about a second versus finding one solution in about 30 minutes. But it's all about how you encode it and throw away the stuff that's not necessary, keep the stuff that's necessary, think a little bit algorithmically and mathematically.
Excellent. I like this example a lot because I think it illustrates what mathematics is. So instead of being focused on the actual concretes in front of you, you're trying to take an abstract view. You're trying to say, for example, when you convert the placement of queens on a board into simply a row of numbers, right? That's abstraction. You're kind of focusing only on one aspect of it. And then you're also representing it with numbers. So you're kind of representing it in a different form than an actual physical piece. So you just have numbers on this little row that you have written on a piece of paper. And that entire, everything that you care about, that particular problem is there on that thing. So I think, so that's, it shows the, what does abstraction mean? I think this is a very good example of what abstraction is. The second thing is to kind of say, notice the pattern that there can be only one queen in a column. So therefore, there can be, no number can be repeated. So you're converting some pattern out there into a law, almost an equation. So that's another thing. And I'm sure the next one would be something like the diagonal. You would have an algorithm for figuring it out. Instead of visually seeing, are there any things, you would have a little algorithm to figure all of that out. So you kind of transposed the problem from the physical world with all its complexities, that this piece is made out of wood, all of that, into an abstract problem, try to look at its properties and its laws and try to solve it that way. Is that a fair way of describing it?
Absolutely. And the representation, it gives you what I would call sort of a fighting chance to solve it a little bit more easily. Obviously, if you just start out and you just write the numbers down, that first, like you just write 1 through 8, that one's not a solution because they're all diagonal. But then you start to realize, oh, I can permute this. I can just come up with some way of generating all of the permutations, we'll say it mathematically or algorithmically, generating all of the permutations, and then I can test each one. Now, an even more clever mathematician than I am could potentially come up with a solution that only generates solutions, that just always says, oh, well, I'm going to generate permutations that are never diagonals. I've never actually gone much farther to see if that's even possible. My intuition is that there isn't a great algorithm for that, but there might be.
Let me point out one more thing that I noticed about this, as this mathematical way of solving the problem as opposed to a concrete way. The concrete way is focused on finding one solution, and then they have to do the entire effort to find another. Whereas with the mathematics, you kind of found a way of finding all solutions.
Oh, sure.
And you just, so you're looking at the entire space of possibilities.
Yeah, and in fact, the algorithm that I used when I coded it, the 8 part of the 8 queens problem was, so I'll say this technically and non-technically. Technically, it was a parameter that I passed in. Non-technically, what that means is that the 8 could have been anything and my program still would have worked. So basically at the top of the program, if you're not programming, I didn't actually do it, but at the top of the program, you could say number of queens equals 20 or 9 or whatever. And it would be a 9 by 9 chessboard with 9 queens, or a 20 by 20 chessboard with 20 queens. There's the abstraction that I don't really care anymore. It could be anything.
Right. Yeah, I think that's another kind of root of the power of mathematics, that when you're approaching things concretely, you're just solving that. In this case, you would solve only one or couple of the possible solutions of that particular problem. And then all the work that you've done is succeeded only in doing that. Whereas mathematically, if you solve the problem, this is a problem to solve this problem from any number of things. And in general, I mean, pattern in mathematics is that people have come up with tools that have found many, many wide uses, because you're moving up in the level of abstraction. So the things to which you can apply your thinking grows dramatically as a result of that. So this was a section on, folks, so this was a section on what is mathematics? And we decided to put in some examples so we could kind of illustrate that. So now what we want to do is that we want to take some questions at this point on the nature of mathematics. What is it? What is mathematics? What is it that the mathematicians do? What kind of misconceptions people have about mathematics? We'll take some questions, and then we will go to the next section, which is going to be kind of more on education of mathematics. So Anybody who wants to ask the question, we've got 4 rules of civility here, which we have used for 4 years. Number 1, raise your hand. You can do that by typing exclamation mark in chat or raising your hand in Zoom. Number 2, keep on topic. Number 3, be brief. And number 4, feel free to disagree with anything anybody says, but do so courteously. All right, so with that, Crystal, you're next. Crystal, go ahead and unmute yourself and you can ask the question.
Right, I usually use my button on my microphone. I forget there's another software mute. Okay, so I'm really interested in this topic. I'm starting out a degree in computer science, and we're the first class, well, it's not the first class. I've taken a few programming classes already and did really, really well in them. However, where there's a class that's got a reputation as being really challenging, and it is a discrete math for computer science. It's a prerequisite for almost the entire program following, and yeah, I'm good at math. It's not like, it's not my, I'm always terribly anxious about math, which is very typically female, as it turns out. I also have half of a degree in psychology, so there's all of this research about, anyway, I'm not going to go into that. But yeah, I feel I get kind of upset when I'm uncertain, and I'm also a strong intuitive thinker. So things don't really make sense to me until they all make sense together. And then at that point, I barely need the formulas. And it's like, this is really easy. Up until then, it seems like I'm just getting pieces, and it's sort of like, this formula does something, I better remember it. I don't know what it does. It just goes aside, and like, oh, I see, it's all connected and it moves together. And that, I don't know if that makes sense. So,
Sure.
But
what's your question, Crystal?
Anyway, yeah, so I'm really interested in this topic. So this class, I know a lot of it is focused on proofs, and yeah, so I wonder, first of all, what's an intuitive approach to mathematics? I've never heard that before, and I wonder if you have any kind of specific advice for a person like me.
Sure. Yeah, I do. So let me say, so I did mention that I do software design and development professionally. I've actually also, I've taught a few computer courses. I've never formally trained in computer science. I'm informally trained. So I taught myself. I had one computer class in college. It was an AI course using Lisp, which was kind of, I mentioned Lisp earlier, but that was at a different time. So I guess the main advice is, and it's really the advice that I give people when they are learning mathematics in general, is to start with a beginner's mind, to sort of empty your preconceptions about what this is going to be. Discrete math is actually very fun. I did quite a bit of it. I studied a lot of what's called group theory and set theory and some of those things. But I think you'll enjoy it, and the application to computers will be good. The intuitive approach to it is relying on sort of what things make sense to you, but how you go from step to step to step logically and intuitively. So applying some logic, but also letting your intuition kind of guide that logic. One of the things that you'll see is that you have an intuition about what a solution might look like, and so you try to figure out a logical path, and the logical path will either lead you to that solution or it will contradict that. And when it contradicts that, okay, well, my assumption, my intuition was off, which is always a good day because you learn something. you know, when you find out that you're wrong, you learn something. But yeah, I don't know. I would just be really relaxed about it. Discrete math is not super hard, and you'll enjoy it.
Next up is Bob, Leslie, Saad, and Bill. Bob, go ahead.
Yeah. How do you regard, when I was in high school, I took plane geometry. How do you regard plane geometry as a mathematical endeavor?
Can you clarify? I'm not sure if I understand what you mean.
Well, plane geometry, circles,
Yeah.
squares, regular polyhedra.
Yeah, really, yeah. Polygons, polyhedra, yeah. Yeah, well, in planar geometry,
rules
polygon.
for proceeding and proving things.
Sure. I mean, so I guess I understand your question. As a mathematical endeavor, it introduces you quickly to the notion of proof. What is interesting is that when I was taught it in school, it was taught from axioms. So axioms, for the folks who don't know, are what we would call base or core assumptions. There would be the things that you would say don't necessarily need to be proved. We're going to assume that these things are true. And then you proceed from those axioms to prove certain things. From that standpoint, plane geometry is great. It can be a little tedious because you learn a lot of construction as well, like how to draw figures and shapes and things like that. It can be a little tedious from that standpoint. The standpoint that is missing, which should come later, but doesn't always come later, is that the set of axioms that you use for plane geometry are not the same set of axioms that you would use for something like spherical geometry or geometry of shapes on a sphere. So think about the Earth being, you know, most of us believe it's round, hopefully. But you know, this notion of it being a ball and the idea that there are certain axioms that you would use in planar geometry. So it's, for example, the parallel postulate. You draw two lines on a plane that are parallel. That means that I can draw lines that will never meet, right? And how does that happen on a sphere? What happens when I draw a line that goes all the way around the sphere? That, you know, is that planar? Is that parallel postulate the same? Does it always work the same way, or on a different shape? And you'll find that there are cases where there aren't parallels, or where there are infinitely many parallels, or that, you know, so on. So from that standpoint, I think it's fine that you learn it and you learn how to do proof. I did think that personally that it got tedious, that it was, you know, doing lots of construction, and that and it might have just been my level of thinking about it, but we could have finished that earlier and moved on and learned some other things. But again, that's just my bias about it, thinking back probably ages and ages ago.
Thank you. Next up is Leslie, Saad, Bill, and Jose. Leslie, go ahead.
Thanks. My comment is not so much about math itself, but how we talk about math. And I like the comment someone made that girls or women are more likely to have anxiety over math. I'm very hesitant to generalize unless there's data to support the generalization. I know that if there is data to support a generalization, I favor generalizations because they help us discuss issues and help us discuss how to solve problems. But like in my elementary school, without a doubt, the kid who was by far the smartest in math and science was a girl.
Yep.
And in my graduating high school class, by far, the two people who were top in math and science were girls. And that's anecdotal, so it doesn't mean that girls are smarter in math. It doesn't mean that boys are smarter in math. It's just, I think we need to be careful throwing disparaging nets out because they limit us. And there's value in discussing generalities sometimes, but I think we need to be careful about statements like women have more anxiety with math, because the way I grew up, of course girls could do math. The best math, you know, a lot of the best math people were girls. And so this idea that girls are intimidated by math, or that the environment and how they're treated intimidates them, doesn't fit with my experience. Mm-hmm. Thanks.
Yeah, that's an interesting comment, and I guess it can be somewhat cultural. That I saw some of that probably early on, but by the time I was in high school, I didn't see it as much. By the 10th grade, I would say, in high school, I didn't see it as much because I was at a magnet school where, again, the best mathematicians in the school, many of them were girls. I will say that it happens occasionally, possibly in pockets, but what my personal experience with math was when I was, I would say pre-ninth grade, is that I was discouraged from mathematics mostly because of my skin tone. I had people even say that, oh, you'd probably be better at something else, and make some comments that I don't want to necessarily repeat, but I was discouraged by adults from pursuing mathematics. That like I said, I don't want to say exactly what they said. It's kind of terrible, but it happens. What I'm glad about it is it doesn't happen everywhere. And I guess in your experience, seeing that it wasn't common was great. But it is cultural. In a lot of cultures, girls do get discouraged, or people of certain skin tones get discouraged. I'd like to not have that happen as much. I work with minority students in Detroit quite a bit, and even some of the parents that I have encountered have discouraged their kids in ways that I just find astonishing.
Thank you. Next up, Saad, Bill, Jose, and Stuart. Saad, go ahead.
Hi, Stacy. Thank you so much for taking this time. I'm sure you all appreciate it. My question is primarily about overfitting. Sometimes mathematicians think that they can model so much that, they're able to guess or predict everything. Wall Street tries to do it all the time. Mm-hmm. And they succeed as well at it at sometimes. So my question basically is, can you give a comment on, yes, mathematics is a language for modeling, but at what point should we try to predict, forecast versus model, try to understand? I mean, there's a very famous quote I remember hearing in Princeton that was economists who use mathematics all the time, is that they spend half the time trying to predict what happens, and then the other half they try to spend it explaining why what they predicted did not happen, because they were trying to use mathematics all the time. So I'm just wondering if you can comment on, at what point do we stop using mathematics and start using, or maybe just leave it up to God, like don't try to play God, or what's that fine gray line?
I'll take a crack at this, and I actually one of my favorite lines is about sort of lies, the three types of lies, damned lies, and statistics. And I think we see some of that. And it depends on the mathematician or the person applying the mathematics. In many cases, actually, I see, especially now, a lot of people applying mathematics in ways that they don't fully understand. So non-mathematicians picking it up enough, having enough, say, computer power behind them to be able to apply something. Machine learning is a really great example of that, and we have in the software industry, people are doing what's called machine learning. It's kind of basically applying statistics and applying mathematics to solving problems. And in that particular space, overfitting is actually a technical term that applies to when you feed an algorithm so much data that your algorithm is great with that data set, and anytime you feed it something from that data set, it gets it right. But if you throw it a curveball, it just gets everything wrong. So that definitely is a problem. I think especially for applied mathematicians, I was a pure mathematician. I didn't do as much application, but for applied mathematicians, recognizing when that's happening is pretty key to solving problems. You don't see it as much in the abstract world because you're not doing things like making predictions and so on. But you do see it in the applied world. Looking at physics is a great example. You may have an approximation of something, Newton's laws, that work really, really well until you start to get to higher speeds, speed of light, and so on. And then you have another theory and another hypothesis or theory, in this case, of how those things work. Mathematicians should be among the first to throw away something that doesn't work. If I have some mathematics and it's proved wrong, I should be okay with letting that go and finding out what is correct. So that's my sort of quick attempt at it. But yeah, it is a problem. I think responsible use of mathematics is to let's look for those things and warn people about them. And make sure that people understand the limits of it and not believe that it's a panacea.
Next up is Bill. Bill, go ahead. Bill, you need to unmute yourself.
Yes, Bill Meacham here. I'm more of a philosopher than a mathematician. My question is, what are numbers? What is a set? What, if you were talking about, you take some postulates and some operations, and then you can do all kinds of cool things with them. Well, what are these things? What do they, for instance, is the number 1 or the number 2, in what sense does it exist? It doesn't have mass, it doesn't, and it doesn't change over time. It doesn't have a front and a back. I mean, it's a very peculiar entity, a number. So what are your thoughts about what are numbers?
Okay, that's an interesting thing, and definitely, yeah, the philosopher meets mathematician, indeed. I'm trying to remember the name of this book. There is a book. I'm going to describe the book, and maybe someone will come up with the title and pop it in the chat. I'm drawing a blank on the title, but it's kind of it's a story about 2 kids who get trapped on a deserted island. I think it's like Anne and Bill or something like that. But if I remember correctly, man, it's probably been 30 or 40 years since I've seen this, but they find something that has a symbol on it, or a set of symbols, and they're starting to try to sort of figure out what this means, what these symbols mean. But the symbols essentially are counting numbers, and they do it with this notion of if there were a number and that number had a successor, say a number that came after it, that gives you a concept of counting, of discrete things, and it gives you a concept of something coming after or being greater than something else, a relative measure, if you will. And they go through and they figure out some basic constructs of number theory based on this notion. So it isn't a concrete thing. It doesn't have a front or back. It doesn't have mass. It is just this notion of an abstraction of counting, of countability or counting, sort of as a process, and the symbols used to represent it. So that's kind of, I know that's a terrible way to explain it probably, but if I could find this book, it's a really fun read. I read it as probably a teenager or shortly after, or yeah, probably as a teenager. But it kind of explains that in non-technical ways. It kind of gets you into this notion of number theory. And then the kids start deriving all kinds of theorems and things. It's kind of funny. It's cute. I really don't, and I'm not in my my home library, so I can't just grab it off the shelf right now. But it's a really thin book, little paperback book. I'll try to find it and let Shrikant know what the title is.
Thank you. Next up is Jose. Jose, go ahead.
Yeah, hi. Can you hear me okay?
Can you speak into the mic here? It's very faint.
A little bit faint.
Yeah, that's my usual problem. I am speaking. Just a second. Give me a second here.
Okay.
Right. So after this question, we're going to go to the next section, and we're going to be talking about few things about the nature of mathematics, and then we're going to talk about education, math education in children and adults, and then we will again open it up to questions. Jose, are you ready?
Okay, I've changed here my setup. Is it any better?
Go ahead.
Yeah, we can hear you well enough.
Okay. My question, I studied engineering, so mathematics was there for breakfast, for lunch, and for dinner every day. And my question was always, after all those years, whether a mathematical thinker is somebody that knows how to execute mathematics, or a mathematical thinker is somebody who actually knows how to use the tools in the toolbox, and not necessarily be the fastest or the, I guess that's the word, the fastest at operating the actual formula. And at engineering school, I saw every type. You have the guys who can be very fast computing the solution once they knew how to solve it. But those people sometimes couldn't solve other problems that other slower mathematicians, to put it that way, or operationally speaking, slower, were able to solve. So my question is this: what is a great mathematician? I don't think it is somebody who executes quickly and knows everything in the toolbox. Is the guy that knows what a hammer is for, what a drill is for, and whether he's good using the drill or using the hammer doesn't matter as much. What do you think?
I think that is a brilliant question and a great perspective. Here's my thought on it. If I had to be great at computation to be a mathematician, I would not be a mathematician. If I had to know all of the nuances of every topic, I would not be a mathematician. I think that you can still be a mathematician and a mathematical thinker, but not be the fastest at computation, not know every nuance. I will give you an example of mathematical thinking as it relates to, in this case, software. And when I was a student, and I think I was 17 at the time, so I would have been a freshman in college, or no, I think I was 18, so I might have been a sophomore. But I started a summer internship at Michigan Bell, which became Ameritech. But it was doing some software design, and one of the things that came up was this idea that they had these rooms full of computers, and what they called back then disk packs. So imagine something the size of a small refrigerator with big spinning magnetic disks in it instead of your little USB thumb drive now. And the USB thumb drive has more storage. And all of these disk packs were out there, and they had networks running to them, basically. They were called IO channels, but networks running to them. And we would watch the traffic on these to decide if we needed to move a file from one of these to maybe another, because that one disk pack was getting way too much traffic and it was slow and the system wasn't performing well. Kind of a strange thing, but similar idea would be, like bank tellers. If one bank teller if there were 15 bank tellers, but only one of them was getting all of the traffic, you'd want to spread that out and maybe open up a few other windows so that other people could go and do those transactions. So many years later, so I had worked on this problem, but many years later, I was using this as an example in a class that I was teaching, a software class that I was teaching. And I asked the students to come up with an algorithm to give me the top 10 utilized disk packs. And there were thousands of disk packs out there. So thousands of them out there, but I only cared about the top 10. And come up with a really fast algorithm for this. One of the students had been trained, actually, this interesting guy, he was a guy from India. He had been trained in computer science, and I had not. I'm a mathematician, like I said. And he came to class and he said, "We never learned that in school." And I said, "What do you mean? You never learned sorting algorithms?" And he said, "Yeah, we learned sorting algorithms, but not that one." And the idea was he could only apply the thing that he had learned. He could apply it really well. So, think of a carpenter could use all of the tools exactly the way they were supposed to be used if he knew exactly what he was building and had built it before. But the mathematical thinker is the one who can take what you've learned and say, oh, I can change this around. I can create a new algorithm that only ever considers those top 10. And it's really a simple one. It's not super complicated. You keep the top 10. If something new shows up, you figure out where to stick it and you throw the old one off the bottom. It's called an insertion sort with pruning, if you're a computer dude, right? He had never learned that. And when we walked through it, he said, "That's amazing. I never would have thought about it. We're not taught to think about it this way. We're not taught to think creatively. We're taught to memorize and to use what we already know." But in my mind, the mathematician or the mathematical thinker is the one who's going to go beyond that and say, oh, I don't care if I've seen this before. I have the tools to solve the problem. So back to my carpenter maybe only made tables forever, but now I approach the carpenter and say, hey, I want you to make a table that has a self-rising top to it, or that has drawers in it. And they may not have made that before, but they know the principles and they can apply the tools to solve that problem.
Excellent. So with that, let's proceed. Let's proceed to the second section.
Mm-hmm.
I want to deal with a couple of questions, partly inspired by questions that have come up.
Okay.
Last time when we talked, when you talked on Monday, you talked about yourself as being, not having a visual approach, but linguistic approach. So can you talk a little bit about what is a visual approach to mathematics and what is a linguistic approach, and what's the difference between them?
Sure. And I think my approach is kind of a hybrid. I do use visualization quite a bit, and I'll draw pictures and things like that. But very often, depending on the topic in mathematics, things can get hard to visualize. When you start dealing with just sort of pure equations or sets, or especially when you start to deal with things that are sort of infinite, like infinite dimensional spaces, or whatever those might be, get a little bit difficult to visualize. So I do rely on visualization to a degree, but I also, in my head, I think about math and programming the way that I think about language. So drilled into me from an early age as a Catholic school student was the notion of grammar. And if I came to you and I said, I am going to the store, it would sound perfectly reasonable to you. If I said, I is going to the store, some people, their heads might explode. Other people might say, oh my God, he's just ridiculous. He doesn't understand English. That's grammatically incorrect. In your mind, you heard that and you didn't jump to, oh, exactly what's the rule. Now, if I subject and verb agreement and so on, you're going to start to think about it as what that rule is. If I push you on, okay, what's the rule? But your ear is tuned to grammatical correctness. This happens to me way too much because there's so many examples in normal speech where people are not grammatically correct, but they're idiomatically fine. That's just the way that people use those terms colloquially or whatever it might be. Data being one of those. We say data is instead of data are, and it's okay. It's a colloquialism. I've gotten over it. I get over it with language. With language, I get over it all the time. But the idea is that there are rules, there's grammar, and there's syntax, and all of that kind of plays in, and you hear it, and you instantly know that there was something wrong with that sentence, even if you don't pinpoint the rule. When I'm doing programming and when I'm doing mathematics, my brain works the same way. And I cannot articulate it exactly because it's not language, but I can give you the analogy of language. I will walk through a mathematical proof and trip up grammatically on something and say, whoa, that was wrong. And I don't know necessarily right away what was wrong, but the linguistic approach in me, that language of math in me says that was not right. That step had a problem in it. And I'll go and dig it apart to figure out what the rule is that it violated. For me, that's kind of that linguistic notion of mathematics and of programming.
Let me ask you one more question. It looks like, because that is your primary mode, or at least the dominant mode.
That's my dominant mode.
So what is what is good about it? What is it that it can do better than the visual mode? I mean, if you wanted to be a champion of that, what would you say?
I don't know that I don't know if there is. It's the mode that occurred to me naturally. It's just the way that it's the way that I started thinking about mathematics before I had any formal training. When I would hop on the bus and go to the Detroit Public Library and pick apart the math books by myself, it was the mode that I was thinking in because I wasn't being taught any other mode. So it's just the one that occurred to me naturally. In programming, and maybe in mathematics, but in programming, what it has done for me is that it's given me the ability to quickly find bugs in a program. I can see something and go, oh, wait, no, this is wrong. It feels wrong. And then figure out what is it violating that feels wrong. It's just a quick way for me to get through it. But I can't argue that a person whose primary mode is visual wouldn't find that a lot, their mode just as effective. Now, I have also had people whose modes were kinesthetic, where they kind of have to use motion and act things out. And I'm having a hard time figuring out how I'm going to do that with certain topological problems where you invert something, but maybe they I don't know.
Excellent. Next question is about artistic sensibility or a sense of beauty and mathematics. So what do you see as a role of kind of a sense of beauty, artistic sensibility in mathematical thinking?
Yeah, and partly this was my my choice in my off topic in the last podcast that we talked on. It was photography. So I'm not. I don't draw very well. I am not a musician. I don't have that kind of innate ability with sort of visual arts that I might have with mathematics. But I understand some of it. I can see what's there, and it can be linguistic, great poetry or literature can have a mathematical sense to it. It can be auditory, where you listen to Bach, for example. People always pick on Bach. Bach had some very mathematical kind of progressions. I can hear it. I don't know the technical terms for it. I'm not a musician, so if somebody were to ask me what it is that I hear there, I don't know. Visually, with things like perspective or repetition or pattern, when you start to see those things, there's a mathematics to that with proportion. You look at certain sculptures and you understand that if the proportions are wrong, if David's head were twice the size as it is, that sculpture would be a farce. but the proportions are correct. And that's where mathematics really comes in. And many would argue, myself included, that mathematics itself has an artistic beauty to it. When you start to see symmetry among equations, when you start to see what's called isomorphisms, or these technical term, look it up, but you start to see that, or you start to see the ability to take what you've learned in one branch of mathematics and apply it to one that was seemingly unrelated, and that symmetry and that beauty there, it's pretty amazing. It goes so far beyond slogging through the times tables that if you learn that first, you'd probably just be like just drooling to learn a times table so you could go further.
Excellent. All right. A quick question I have to ask. Why, in terms of mathematicians, you said Gauss is your favorite mathematician. Why?
Oh,
what,
sure.
what do you like? What do you like about him?
Sure. Yeah, I'll answer that. And by the way, someone put in there, David's proportions are heroic, not standard. And that's absolutely right. And I wasn't saying that they were standard. What I was saying is that if his head were twice as big, it would look weird, right? So, getting the proportions to be artistic, they don't have to be accurate. They have to be artistic. Then there are other artists who intentionally distort proportion to make an artistic point, and that's cool. That's all part of it. So yeah, that's a really great comment. I appreciate that, because it definitely definitely the point that I wanted to make and may not have made as eloquently as I had wanted to. So I really appreciate that comment. I'm sorry, I'm not following the comments very well either. But, okay, so
Stacy, you don't need to pay attention to the comments.
Yeah.
What we'll do is I'll give opportunity for people to ask the questions directly. Let me do one thing. We're running short of time, so I'm going to jump to the next question. We'll
sure.
to Gauss later on. We'll talk about him at another time. So in terms of education, now you have been tutoring kids for decades now, right?
Yep.
For a long time. I'll ask a two-part question. You can take whichever part in whichever order. So one part of it is, how do you develop love of mathematics in kids? That's one. And the second is, how do you communicate the value and the beauty of mathematics to people in general so that they will support the mathematical education of their kids?
Yeah, that second part is harder. So with students, I try to, depending on their age and depending on their predisposition, some of my students come in wanting to know and learn and loving math, and we just make it as fun as possible. Others, in either case, and others come in with this, I just want to get through the next test. I don't want to learn this. My parents, were bad at it. And so they, especially when I was in high school and college, I tutored a lot of friends' kids where the parents were just not that great at it. What I try to do is break them of the notion that it's hard and that they can't do it. The hard part is, if you aren't willing, my analogy, if you go to the gym saying, I'm going to build muscle, but you only ever lift a 3-pound weight, you're not going to build a whole lot of muscle. If you challenge yourself and push yourself out of your comfort zone just a tiny bit, and that's what I ask people to do. I just say, give me just a little tiny bit of you going out of your comfort zone and making your brain hurt. Just a teeny tiny bit. And then the payoff for that little tiny bit will be enormous. If I can instill that in a student and get them to just push that little bit more, and whatever their hobbies are, their loves, if it's sports, if it's music, if it's whatever, put in the effort that you would put into that, just a fraction of that effort, and you're going to get a giant payoff. And for the parents are the harder nut to crack, because the tough ones are the ones who, quote, hate math and aren't good at it, and they put that on their kids. They say, well, it's hard, I get it, it's okay if you don't do that great. And it's not okay. It's not okay if they don't do that great unless they really tried. But what you're doing is you're giving the child permission to not even try, to not even put that little effort into it. So I try to get parents to realize the value that their own children will have from that.
Let me ask a question, a general question. What do you think is the role of mathematics in culture? What has mathematics done for us?
Oh, wow, where do I start? Pretty much everything. And my tendency on that question is to go to the applied math, because I think that's where most people will see the value right away. And I will defy any person to get up in the morning and go an hour without using something or some principle that mathematics hasn't influenced. From running water, to eyeglasses, to electronics, to books, to living in a house that doesn't fall down. There's mathematics behind everything. You know, we use math every day, almost every moment in our lives in some application. Beyond that, I think it has taken us to places where we can start to theorize, where we can have things like theoretical physics, where we can use mathematics to predict what will happen in a reaction chemically, where we can create drugs that will help to cure diseases. You know, all of those practical applications and those theoretical applications all stem from mathematics, which crazily enough all stem from I need to count how many cows and sheep and chickens I have.
Yes, absolutely. You know, now if somebody wants to, is convinced that, look, I really need to know what mathematics is, kind of develop some appreciation of it, but I'm starting at a very low level. What would you recommend? What would you recommend to a layman to learn about, you know, to really understand, you know, to get some sense of mathematics? Where do you start?
So depending on the person and their goals, one of my favorite starting points is mathematical games and puzzles, because it's a fun way to approach math that's not threatening, and it's okay if you get it wrong, because it was just a puzzle or a riddle or a game anyway. So that's a really non-threatening way, and you learn lots of different techniques about how to think when you solve those puzzles, or even when you fail to solve the puzzle, and you can apply that thinking the next time through. That's my favorite way to start. If you want a more technical introduction, then I would look for some of the things online like the Khan Academy. Socratica is a YouTube channel that has some really good series on mathematics. They kind of jump in the middle in some of them, but most of them, they start from core principles. And there may be some other ones out there too. But I definitely, depending on your goal, start with puzzles and games. They're great.
Yeah, I would love to do, you know, talk more about puzzles and games. I mean, I think for me also, Martin Gardner was a big influence. You know, his puzzles, I mean, just the range of it, and just even the fact that he could take a very simple thing like Lady and the Tiger puzzles and produce this immense variety of problems. So wonderful. So I'm going to leave some time for questions. So folks, you can go ahead and line up for questions. People who have not asked the questions will get priority over people who have asked the questions. Please try to keep the questions on the topic. We're talking about mathematics and mathematics education. And let's go from there. So the first one up is Crystal. Crystal, go ahead.
Hi, I actually have two questions which might which are perhaps a bit involved.
Sure.
So,
please keep them brief. Go ahead.
All right. So, well, yeah, two things. So perhaps I'll just say them both. I'm interested in this idea of grammatical sense to numbers, and I'm thinking about, as I do have some experience with proofs, not extensive at all, but I took a course where we learned some imaginary numbers and things like that. It was an optional course, and I liked it. But yeah, I remember on the final, there was just this one step that I'd forgotten, and I kind of panicked.
Crystal, we've got about 25 minutes before the next meetup starts, so we don't have much time. Do you have a general question about general mathematics or mathematics education?
Is there any way to talk about this some more with you?
Absolutely, absolutely. We'll continue this. We'll continue this another time. Okay, Laura, you're next. Laura, you need to unmute yourself. Doesn't look like. All right, Crystal, Laura is not unmuting, so you can go ahead and ask a quick question. Okay, Laura, go ahead.
Okay, I think about creating patterns, and I had it a second ago, creating patterns and oh God, mathematics about creating patterns. Forget it. I can't. I don't remember the one sentence I had in my head.
Okay, sorry about that.
Take your time, and we'll hear it.
Take your time. If you have something, you can go ahead and ask again. All right, Johanna, go ahead.
So I was the one who made the comment about the hero proportions of David, because when I first learned that, discovering that what we see and like in art, like the proportions, human proportions versus artistic proportions being different. And the math of that was surprising, but also kind of beautiful to me. Mm-hmm. Because in art, you have to learn how to draw what you see. And then learning all sorts of different things as far as how math and physics are embedded so many different ways, but in some ways it was like breaking the rules, but also not breaking the rules. And so my question is, in your experience, what are ways that math is giving us rules that are breaking rules, if that makes any sense?
I think it does. It may, in my mind, be more like giving us rules that bend our perceptions.
Yes, thank you.
Where, for example, you talked about proportion, understanding how to change proportion in a way that has an impact on how we think, that has an effect on us, but it's the intended effect. So, if David had one clown foot and a giant head, that's exactly the intended. You'd probably laugh. You would say that's a ridiculous thing. But if David has heroic proportions, and we know and we understand what that means, and we study what does that mean, then it has a different effect. It's wow, this is a powerful figure. So I think that what math does is not necessarily break the rules, but it bends our perceptions and it changes how we view things. I find that when I photograph, so my hobby is photography because, again, I can't draw. And I find that just changing my perspective on a scene can change a scene from mundane to interesting, moving up or down or left or right, or how I hold the camera or what lens I choose will change the perspective and the proportions of the image. And I don't necessarily think of it when I'm doing it as mathematics. I think of it more intuitively than that, but there's math behind it, and there's mathematical thinking behind it.
Like the way that your eye travels across the screen, it focuses on these points.
Yep. Yep. We actually did a really, so there was an interesting study of that, looking at art and using what's called a gaze tracker. So when the person would go up to a piece of art in a museum, the gaze tracker would track where their eye moved and how long it stayed in particular places on an artwork, on a painting. And it was really interesting to see how people kind of examined the whole thing, but zero in right on what was sort of the main topic or subject of the art, and how that works in different works of art and with different artists. And some artists have so many little details that people would spend a lot of time in the periphery figuring out what all those details were, and other artists would just leave out, you know, all of those details on the side and just have detail in the central subject. So it's pretty interesting to see.
Okay, next up, Diego had Margaret, you had a question?
Yeah, yes, I do. I'm sorry, I don't know how to do this chat thing very well, if at all. I wanted to ask what you thought about Max Tegmark's idea of that we're all just a numeral, you know, this abstract number thing.
I love Max Tegmark. He's way smarter than I am. He has some interesting ideas and some interesting concepts. What comes to my mind is, does that give us an abstraction that's useful? Can we use that to think about things and to reason about things and to further our knowledge? Or is it just sort of kind of interesting and fun to think about? And that might be enough as well.
Yeah, but I mean the whole concept that we're all just sort of a virtual creation of some other civilization.
Yeah. I mean, to break it down even more, it's almost like thinking that we're a computer program. So I don't know that it's provable, but if it were, there's actually a really funny kind of comical book called Off to Be the Wizard. Not off to see, but off to be the wizard, where the character discovers that, hey, we are in a simulation, and that character inside the simulation learns how to control the simulation. And yes, Shrikant, it is fiction, but what's interesting is kind of, okay, if you know that, what comes after? What ensues from that? It's silly comedy. It's not really a heavy-duty read, but it's kind of fun. But yeah, I don't know if I agree or disagree with Max. I don't know enough to know that I could agree with that because I don't have any evidence.
Next up is Diego, along with Joel, Diego, and Helen. Go ahead, Diego. You had a comment.
I think there is a problem in mathematics regarding education, and there is a disjoint between the technique or the procedure, the mathematical procedures, and the meaning behind the techniques. For example, a simple example is solving general students, the elementary students have problem with the fractions. So they can learn the technique that to add the two numbers, half and 1/3, you need a common denominator, which is 6, and then you can add 1/2 plus 1/3. Okay, that's the technique. However, the students has a problem to learn the technique and solve the problem, but not having the meaning behind. So this becomes, of course, magnified when, for example, you're trying to solve a partial differential equation. So I have the technique how to solve, and I got my honors degree in mathematics, did very well because I learned the technique. But really, I didn't know what that equation actually meant. So, for example, geometry or whatever, especially. So I just learned the technique. I solved my partial differential equation without knowing what actually the meaning behind that equation. And that's the dichotomy that there is in education regarding mathematics. So the good students, quote unquote, good students, can pass all the courses, even at the postgraduate level, by just learning the techniques. But the true mathematician really understand the meaning behind the technique.
Yeah, you're
Or the
absolutely right.
procedures, if you don't like the word technique.
I absolutely agree with you. And I think that's the difference between knowing an algorithm or being able to just reproduce a result and actually have some creative thinking and understanding the abstraction. To me, the most value is in the abstraction, and I agree with you. And I believe that's one of the shortcomings is that we don't give kids enough credit. So kids are born scientists. Kids are curious. They are capable. A child has a brain that is just an amazing instrument. They are, as Elon Musk says, they're the OG neural networks, right? And look up the slang if you don't know what OG is. But they are, they're really, really capable. And we don't give them enough credit for that capability because we impose our own limits, the limits that we may have learned later in life. We impose those on kids. I believe that they can learn abstractions really quickly, as evidenced by the fact that they learn languages really quickly. The fact that a child can learn multiple languages at a very young age really quickly through exposure means that they can learn these other abstractions as well.
Excellent. Next question is from Stuart. He was asking about Martin Gardner and mathematical puzzles. So what would you recommend, if somebody wanted to look at mathematical puzzles as a way of getting used to it, what would you recommend from Martin Gardner?
I would pick up any of his books. When I started reading Gardner, it was through Scientific American. When I was probably in the 8, 9, 10 range was when I started reading Scientific American. And we ended up getting a subscription to it because I loved it so much. But when we didn't have the money for a subscription, I would, scrape up money and buy copies. But that's where I got my exposure to Martin Gardner. I would go to the library, read the issues that I didn't have. And then when he started coming out with books, which many of the books were collections of his puzzles from the magazine, but then there were also books that had new ones and different ones. Later, I think it was, Douglas Hofstadter took over the column and slightly renamed it. I also put a link to Hofstadter in the chat. He's got some great books out there too. But his are not puzzles. His are more math and metamath. Anyway, I would look at that and just any of the books that are out there on mathematical puzzles, not just Gardner, although he was one of the best. Try to find those books. There are some okay websites. I've not had as much great luck with the websites, but that just may be my search skills as I have with the books.
Yeah, excellent. I mean, I personally like work of, Kevin, what is it, Devlin.
Oh, yeah.
Devlin. Yeah. It's I keep going back to him because I find it's a very interesting combination. He's able to actually give you a sense of what it meant. Like, for example, for preparation for this, I was reading his chapters on calculus. And the book I really like is Mathematics, the Science of Patterns.
Right.
And what he does is that in very simple language, he's actually talking about why calculus. What is it that it does and what is its place, and actually takes you through the steps.
Right.
It is on one hand accessible, and on the other hand, it's the real thing. He's trying to give you what it actually means. So it's remarkable.
Yeah, definitely.
Next one is Christine. Christine, go ahead.
Hi. So I'm not sure if this is implemented throughout all of the world or at least North America. In Canada here, in my location, they have implemented a new form of math. Now, this way of calculation is completely foreign. They actually had to have workshops for parents to go to so they can help their children understand this new math that was implemented. Now, how do you feel about this new age form of recreating something where the rest of the world is still in the normal math and this new world is in this unknown? how do you feel that's going to impact the continuation of mathematics for all the generations that are trying to work together?
Well, it's interesting because you called it the new math, and I want to get a better understanding of what they're doing in Canada that's different.
So
yeah.
Instead of going the way we learned, which was 250 plus 350 equals with a line underneath.
Yeah.
Now they write it in series.
Oh, sure.
It's a very, I would say that there's a little bit of implementation from I think it's finite in that type of it's not calculus, but it's the one before. I believe that's finite. So it has implementations of series going on,
okay.
But it is written in a way that there's several lines of processes in order to find the way that we would normally calculate, which is going top down with addition, just as an example. So
yeah. So you probably go top down, right to left, don't you?
Yes, that's correct.
Yeah, that was my issue when I was learning math in school, is I didn't do that. I actually intuitively taught myself to go left to right and have only one intermediate result and not have to kind of keep intermediate results in my head. I just write down things as they happen. The difference, and what you're talking about is that's really just arithmetic. That's just a different way of looking at arithmetic. There are all kinds of clever algorithms that you can use. You can write things in a grid, and you can start having intermediate results in the grid. And what I think about that is, yeah, let's learn a whole bunch of different ways to do it and figure out which one works best for you. When you mentioned the new math, that was actually something that I learned in school. When I was in grade school, they called something else the new math, but it was just set theory. We started learning about sets, and we learned about modular arithmetic, and we learned about a bunch of things like that. They call that the new math, but it was really just trying to take kind of an interesting approach. It was fun for me, but an interesting approach of teaching these kind of axiomatic approaches to building up mathematics from set theory. I don't think it was a successful experiment, but it was an interesting one.
Thank you. So we're coming to the end of this meetup, because we have another meetup starting up at 2:30 on different kind of human functions. What is it that human beings are capable of? And people are going to bring different kinds of ideas, and we're going to discuss them. So that's what is coming up. So Stacy, we have like about 5 minutes to wrap up. What would you like to leave people with?
Well, mostly with a challenge. So if you are not yourself sort of a math lover, or if you are a math lover and you know someone who's not, take up the challenge, push yourself that little tiny extra bit to get your brain a little bit uncomfortable, and sweating a little to think through a problem, to learn some mathematics, get some puzzles, get some games, challenge friends to these things, and maybe even in a community of people, get together with other people who maybe know some math, if you know some mathematicians around, or people who want to learn it, almost the way that you would do with a book club, so that you can push your skills a little bit. And if you need to, apply some of that stuff to the real world, if that helps. It can help, but use it to understand really things that are going on in the world. If you listen to the last podcast, I gave an example that I think would be interesting. It's what I call the bacon sandwich problem. But people learning about statistics, learning about mathematical thinking, I would say, those would be the things. If you started math clubs that were like book clubs, that I would be so thrilled.
Wonderful. Well, thank you very much, Stacy. This was just incredible. and look forward to continuing the conversation.
Right.
And thank you very much, everybody. It's always, I'm always grateful to see all these amazing people show up from all over the US and sometimes from the world to have this back and forth discussion. So thank you very much. We'll take a short break of about 3 minutes and we will start the next meetup then.
All right. Thanks, everybody.
All right.
Bye.
Bye, Stacy.